So formally, this equation rho I dot minus I hi rho I can be solved as follows. Rho I at time t will be rho I at 0 minus I integration h I s rho s ds from 0 to t. So here we have solved for rho I in terms of rho I. So it's a recursive solution, and we can substitute rho it in this expression to get the second order. So rho it becomes rho I 0, rho I dot again becomes minus I hi rho I 0 minus I 0 to t hit his rho s ds. This is the recursive solution of the dynamical equation in terms of rho I. Let us drop the subscript I. From here on, every state and Hamiltonian is in the interaction picture, so we don't need to write subscript I, which represents the interaction picture, and this will make the expression a little bit simpler. Let me write it clearly here: minus I h t rho 0, and there is a minus minus, so it is just minus I, there is just minus sign, 0 to t ht commutator hs rho s ds. We are assuming that the interaction between the system and bath is captured by the interaction Hamiltonian. The interaction is weak and parameterized by a small parameter lambda. So the interaction Hamiltonian hi depends directly on lambda. And lambda is so weak that lambda square, any term above lambda square can be neglected. So we can stop this evolution, or we can keep the dynamical equation up to second order in the interaction Hamiltonian. So we don't need to go beyond this term. Another thing, the interaction Hamiltonian hi can always be written as the operator in operator acting on the system Hilbert space A alpha, tensor operators acting on path Hilbert space B alpha, and sum over alpha. Any operator acting on HS tensor HB can be written in this form for appropriate choice of A alpha and B alpha. And let us assume that A alpha and B alpha are Hermitian. So A alpha dagger equals A alpha and B alpha dagger equals B alpha. One assumption we have here for the open system dynamics is that bath is completely random. Bath is random. What does it mean is, if we have the state of the bath as rho b, initial state, then the expectation value of all the bath operators B alpha will be 0. So it's a maximally random state. The bath is always in a maximally random state, so that no information can be extracted from the bath. It means the bath operators we have used in the expansion of the Hamiltonian, the interaction Hamiltonian, the expectation value of those bath operators is 0. This is what we will call as the bath is completely random. From here we can calculate the interaction Hamiltonian in the interaction picture, which is R hi R dagger, where R is exponential of I hs plus hb t. So Hs and Hb commute, so we can always write R to be exponential of I Hs t times exponential tensor exponential of I Hb t, which is equal to, which can be called Rs tensor Rb. So from here we can calculate Hit as sum over alpha Rs A alpha Rs dagger tensor Rb B alpha Rb dagger, where Rs and Rb are the exponential of IHST and exponential of IHBT respectively for the system and the path. Let us call R B alpha R B dagger to be B alpha dagger, the time dependent path operators. And similarly, Rs A alpha Rs dagger equals A alpha T as the system operators. So Hit can be written as sum over alpha A alpha T tensor B alpha T. Next is the Born approximation. In open system dynamics, typically we assume that the bath is so big as compared to the system that the state of the bath does not change just because it is interacting with the system. On the other hand, the system is very small as compared to the bath, so it will see some changes which will be calculated in the dynamical equation. So Born approximation states that rho system and bath, the total state of the system and bath at time t, can always be approximated as state of the system at time t tensor the state of the bath, which is constant throughout the dynamics. So let me restate that the Born approximation says that the bath is so large as compared to the system that the state of the bath does not change as a result of the interaction with the system. So the state of the bath remains same throughout the dynamics, but the state of the system changes with time. So total state of the system and bath can be approximated as a product state between the system state rho s at time t tensor the steady state of the bath rho b. This implies that the rho s dot, which was traced over rho sb dot, the time derivative of the rho sb, will be is minus I trace over path H T. We are suppressing the subscript I rho S T tensor rho B minus 0 to T ds H T commutator H S rho S S tensor rho B. Let us look at the first term. The first term, the commutator is HIT rho ST tensor, it's rho S0, it should be at 0 time, tensor rho B which is sum over alpha A alpha T tensor B alpha T rho S tensor rho B minus sum over alpha minus rho S tensor rho B times sum over alpha A alpha of T tensor B alpha of T. And then we take trace over the path, trace over path. When we take trace over path, it becomes sum over alpha, A alpha, rho S, tensor trace over beta alpha T, rho beta, rho B, minus rho S, sum over alpha, A alpha, tensor trace over rho B, B alpha T. So this is the expectation value of the path operator at time t, and this is also the expectation value of path operator at time t. Since the path state does not evolve in time, it's in a steady state, so this expectation value is same as the expectation value at time 0. And since the path is considered to be completely random, this tends to 0. Therefore, the first term itself goes to 0. And we are left with the simplified dynamical equation, that is rho s dot equals trace over path minus 0 to t ds. This is the time, this is the integration, s is the integration parameter, h t commutator h s rho system at time s tensor rho path. Our task is to simplify this equation and bring it to a simple form. We can expand it to be trace over b minus 0 to t ds, commutator of ht with hs rho s s at s tensor rho b minus rho s rho b times hs. This is the time s. And this can be written in terms of, this can be written as minus 0 to t ds. There will be 4 terms because it's a commutator of 1 with the 2 terms. It will be ht hs rho s at s tensor rho b minus rho s at s rho b minus hs rho s at s tensor rho b times ht. This is the first term. And the second term is minus ht rho s at s tensor rho b hs minus rho at s at s tensor rho b hs ht. So these are the 4 terms we have. So we have to simplify all 4 terms to get the final expression for the dynamical equation. We take the first term alone. The first term is the first term I'm writing here. So the first term is ht hs rho s at s times rho b. We can expand ht and hs in terms of a alpha and b alpha, and we get sum over alpha beta a alpha at time t tensor b alpha at time t a alpha at time s tensor b alpha at time s rho s at s tensor rho b, and then there's a trace over We will worry about that later. Now we use ABCD rule of tensor product. Let me remind you that rule. If we have A tensor B times C tensor D, then we can write it as AC tensor BD. So using that, we can write it as alpha beta A alpha at time t, A beta, should be beta here, not alpha, at time s, rho s at s tensor, B alpha at t, B beta at s, and rho b. Now if we take trace over B here, then we get sum over alpha beta, A alpha at t, A beta at s, and rho s times the expectation value of B alpha at t and B beta at. So the first term, that is ht hs times rho s rho b traced over the partial traced over the bar degree of freedom results in an expression of expression in terms of A alpha, A beta, and rho s, and the expectation value of the product of two Bell operators, two Bath operators, B alpha t and B beta s. And this is the 2-point correlation function in time of the Bath operators. So B alpha at t, B beta at s, which is trace B alpha at t, B beta at s, and rho b. This is the 2-point correlation function of Bath operators at time t and s. And let us call them C alpha beta Ts. So using this, we can write the dynamical equation rho s dot s minus sum over alpha beta integration 0 to t ds. There will be 4 terms here, and those will be A alpha at t, A beta at s, rho s at s times C alpha beta, and I'm just suppressing t and s here. The next term will be A beta of s, rho s at s, and A alpha at t, C alpha beta. That was with minus sign, minus A alpha of t, rho s at s, A beta of s, C beta alpha plus rho s at s, A beta at s, A alpha at t, C beta alpha. So C alpha beta is a function of Ts. So C alpha beta is a function of Ts, and St and St. Okay. So our dynamical equation in terms of rho s looks like this, and you can see that the right hand side depends on the 2-point correlation function of the path and the state rho s of the system, along with the operators A alpha and A beta, which acts on the system Hilbert space. So in general, this equation is difficult to solve. To make it easy, we will apply some approximations, and those approximations we will explain one by one. The first approximation we have is that C alpha beta Ts is delta T minus S. C alpha beta at Ts is proportional to delta T minus S. It's a delta function. What it means, it's an uncorrelated path. It means the correlation in the Bath operators at time t and at time t prime or s is 0. So the correlation we can see only when the two operators are at the same time. Therefore, we can write C alpha beta Ts times rho S to be same as C alpha beta Ts rho S at T. So this is the property of a delta function, that the delta function times any function at time S is same as the same delta function and the other function at time T. Using this, we can write that the dynamical equation for our system state as some superoperator, some map acting on rho s of t. Unlike what we had so far here, where the rho s at time t, the derivative of rho s at time t depends on rho s at time s, some other time s, and that s can take value from 0 to t, any value from 0 to t. But with this approximation that the path correlation dies very fast in time, we can make the dynamical equation local in time. So this time local dynamical equation is called Redfield equation, and here the state at time t depends on the state at time t, but it considers the correlation functions from the earlier times also, because the integration still depends from 0 to t. So the equation is local in time in terms of the state, but it still has the information about the history of how the state was evolved. So in that way, it's not a Markovian master equation. Markovian dynamics is something which does not depend on the history. So if we have a quantum system rho, and let us say it's in some parameter space, and in time it evolves, the state evolves using taking some trajectory in the parameter space. So there is some state rho s. This is rho s at time t, and it takes this trajectory, let us say. If we have some state here at rho s at, let's say, t0, and we forget about this system, we take another quantum system and prepare the state of the system in rho s t0, and then we evolve it with this Hamiltonian, this open quantum system dynamics Redfield equation, or whatever dynamics we have. If it takes the same trajectory again, irrespective of where we started from, then it means the dynamics of the system does not depend on what path the system took to arrive at the state rho s t0 for any t0. It means there is no information about the history of the evolution. In that, those kind of dynamics are called Markovian dynamics. But the Redfield equation in general does not satisfy this condition. In Redfield equation, if we start from state rho s t0, it might take something else, some different trajectory altogether. Similarly, from some other point, if we start, we'll reach somewhere else. If we start from third point, we will go somewhere else. So the future dynamics of the quantum system depends on the history of the state. So if we start from here, we will get the original dynamics. If we start from somewhere else, then it will be we will end up getting some entirely different state. It is possible in Redfield equation. In order to convert the Redfield equation into Markovian dynamics, we need to make some further simplifications. One of the simplification is that we take t equals 0 to t equals minus infinity. That is, we say that our dynamics does not start from t equals 0, but it starts from t equals minus t tending to minus infinity, and we can say that the interaction Hamiltonian for t less than 0 is just 0. So there is no Hamiltonian, or the interaction between the system and bath before the time t equals 0 was 0, and after the time 0 it was some hi was given by some over alpha A alpha t tensor B alpha t for t greater than or equal to 0. And for t less than 0, the interaction Hamiltonian is 0. So there is no interaction between before t equals 0, and the interaction Hamiltonian is given by this after t equals 0. It means we can write d rho s over dt to be 0 to t ds means the factor we had calculated the expression plus 0 because the interaction Hamiltonian is 0. This can be written as minus 0 to t ds times the factor plus 0 to minus infinity to 0. Let's put minus sign here times ds times 0. We can write it from minus infinity to infinity. So t ds times the expression in terms of the interaction Hamiltonian hi, and hi is given by these two conditions, that it is 0 before t equals 0, and it is given by this expression for t greater than or equal to 0. Second simplification we make is that we define a parameter tau such that s is t minus tau. This implies that when s equals t, that is the upper limit of the integration, then this would imply that tau is 0. And when s tending to minus infinity, then tau tending to infinity. So we have defined tau as a function of s, or s as a function of tau, such that when s is t, then tau is 0, and when s is minus infinity, then tau is infinity. So the integration limit from minus infinity to infinity will become minus of d tau 0 infinity to 0, and that will be 0 to infinity d tau. These two simplifications put together will convert the Redfield equation into a Markovian equation. And we get the dynamics rho s dot t to be minus 0 to infinity d tau h of t commutator h of t minus tau rho s of t tensor rho b. So this is our dynamical equation when we substitute s with t minus tau, and we assume the path correlation functions are fast decay. This is a Markovian master equation. And this we reached by using Born approximation also, though it's also called Born-Markov Master Equation.